Capacitors do not instantaneously charge and they do not instantaneously discharge, and this actually means that they can be useful in circuits where we don't want a steady state current even though they're hooked up to a DC source. So like imagine your windshield wipers, they need to intermittently cross the windshield, or a blinker that turns off and on and off and on. We can use a capacitor to do that, because what happens is initially if we were to close this switch, current could start to flow until this capacitor had reached an EMF equal to the EMF of the battery, or a voltage, I guess, equal to the EMF of the battery. So our load here would actually initially, if this was a light bulb, it would initially light, and then it would go off. And then we would need some way to discharge this capacitor, and then we could get current to flow again, right? So this circuit by itself can't be used for that, but it's the basis of that. And what this graph shows is actually how the voltage across the capacitor changes in time. E is the EMF, or electromotive force, of the battery, and VC is the voltage of the capacitor. And we can see that as time goes on, the capacitor reaches the voltage of the EMF, and that's when current will stop to flow. And so what we see down here is how long it takes to reach certain milestones. So the time to get to 63% of the EMF is RC, where R is the resistance of the resistor hooked in series with this capacitor, and C is its capacitance. At 2 RC, we have almost reached capacity. 3 RC, we are essentially there, although this is an exponential decay graph, so it turns out that to really get this to work all the way, T would have to go to infinity, but we're close enough after 3 RC that it doesn't really matter. And then this is the current. Remember, voltage divided by resistance, right? V equals IR. So if I divide both sides by resistance, I get the current. So that's what this is showing. This is showing the current through the circuit as voltage divided by resistance, and we can see initially the current is really high because there is no impedance from this capacitor, but as time goes on, current gets less and less until again current stops flowing. So these graphs show the potential difference across the capacitor and the current in the circuit as time goes by. Now you might have noticed on that graph that these times were given as RC. That's called the time constant of the circuit, and we can actually give the voltage as a function of RC and time. So this E is Euler's constant, or then base of the natural log. So if you've ever seen natural log ln, that's log base E. We're going to have to deal with that a little bit in some math, but we'll get there when we get there. This exponential decay equation, that's the equation that describes this function right here, and so we can rewrite that equation to get it in terms of charge. So the maximum charge on the capacitor times this decay gives us the charge at some time t, and this RC constant is just dependent on the circuit, depends on the capacitance and the resistance in there, and so this should say 63% of its maximum charge. So the time constant gives how long it takes the capacitor to reach 63% of its maximum charge. We will work an example problem on that in a different video. Okay. Now, the resistor voltage and the current. So now I want to look at, okay, so if we just described the voltage of the capacitor, how is the voltage of the resistor related to that? Well, remember, around this loop we have positive voltage here, and so negative voltage here, and those have to add up to 0. So that's what I show here. The EMF of the battery minus the voltage of the capacitor minus the voltage across the resistor, that is 0. Solving that for the voltage of the resistor is just add this over to the other side, which gets us this. But remember from the previous slide, the voltage across the capacitor is given by, pull that equation up, this equation right here, right? So E times 1 minus e to the negative TRC, and then we're subtracting that, so 1 minus becomes minus 1 plus, and so 1 minus 1 because we factored out this E, it leaves us with just e to the negative TRC. So the voltage across the resistor at any time is given by the voltage of the source times e to the negative TR over RC. And again, if we want the current through the resistor, we would just have to take and divide the voltage across the resistor by the resistance, because V equals IR. And so this would be I equals the EMF of the battery over the resistance times e to the negative T over RC. Now, the last thing that we should talk about is discharge, right? So here we've hooked up a battery to a capacitor and current flows until it doesn't. What happens if I have a charged capacitor and I hook it up to a load? So here you've noticed the voltage source is gone and I just have a capacitor that is already charged and has some initial voltage. If I close that switch, then of course this is going to discharge. It's going to discharge by flowing through that resistor, converting this electric potential energy that's stored in the capacitor into heat or whatever this load is. And so the charge that we start with is called Q0. That's our starting charge in the capacitor. The charge moving at any time is given by this equation, or we can say the voltage across the capacitor is decreasing. It started at some initial voltage, and then we use this exponential decay to model its voltage at any time t after it has started to discharge.